Good evening, everybody. Welcome to this Asset Condition Assessment webinar. This is the sixth series, the sixth session of the 7-part series. My name is Refilwe Buthelezi, and I will be your moderator for today. Okay. I am an automation asset manager at Water, and our presenters for this evening is Engineer Moyo, who is a general manager at the Power Delivery Engineering at Eskom, and Engineer Nxuamal, who's a pipeline asset manager, my colleague at Water. Our presenters this evening will present a structured risk-based approach of identifying assets that have reached economic end of life. Please enjoy the webinar, and you are more than welcome to post your comments or questions in the question pane. I will now hand over to Engineer Moyo to kick us off.
Colleagues, comrades, and friends, thank you very much for joining us. I see the turnout is looking good. It's an exciting topic, one of my favorite, because this is where the rubber hits the road in terms of existing assets. So I'll be covering this topic for you from an electric utility perspective, and Aubrey will give you a little bit towards the end on water utility context. This is what I'll be covering, some aspects on physical assets and capability. As transmission assets we saw when Teboho presented last time, then concepts of asset health and asset risk, and then really asset renewal decisions and prioritization, and then I'll summarize for you. So we have this on the right-hand side here, this asset lifecycle view that we are on about in asset management. Needs identification, pre-acquisition is preparation and tasks like engineering. Then acquisition includes the construction and commissioning, logistic support during the life, and then operating and maintenance. And finally, we give up and we say end of life. And maintenance was covered by Teboho in one of the webinars. These two here, growth and expansion, as well as operations and flexibility, were covered by Leslie and Martin, my colleagues also from Eskom, and I'm covering today this concept of end of life. This slide you would have seen in all our presentations is basically just to orientate you in ISO 55000 with respect to where we are. All these engineering clever analysis and studies are done in this block here of asset management plans, which fits in nicely with the strategic aspects such as the linkage with the organizational plans and objectives, understanding our stakeholders. Then we do the clever engineering package projects for implementation, and then we do performance evaluation. So it's plan, do, check, act, plan, do, check, act, and so on. So this is the definition on asset renewal or refurbishment. You may not find it in a textbook. I've used a lot of sources to try and present concepts that relate to this thing here. And it's investment. It's an asset whose technical performance has deteriorated. We say so much that it has reached end of life, and that end of life is very subjective, which is why you need a scientific approach. There's some restoration to it. You generally get limited improvements to functionality. You are restoring after all, and generally you don't change the original design of the asset. The first concept I would like to cover is this one of physical assets and capability. Of course, you can see that with the graphics here, some assets end up becoming incapable. We start off with design performance. Again, this picture you'd have seen from Teboho. I'm deliberately using a slight version of that slide so that I reinforce the concepts. We start with design performance when we roll out the asset, but of course, you know, on the right-hand side here, I say I wish our assets sometimes could get better with age, like good wine, but unfortunately, you never get such an asset. You always have a threshold of a minimum performance, and you can be sure that your asset is going to deteriorate in performance, which is why we do maintenance to restore some of the performance that deteriorates and eventually give up when we have passed the minimum performance stage, and then do investment. Another view of capability of an asset, you will see the solid steps which go to the bottom are in fact talking about some lost capability which needs to be replaced, whereas the dotted line going up presumes that you are growing, because after all, that is the intention of every business, to grow so that you keep ahead of your costs. So that's what capability covers. On the bottom line of the straight line, which is the design capability, is really investment to ensure that you have reliability through maintenance primarily, and sustainability through asset renewal. But with the dotted line going up, you are covering growth, new demand, as well as flexibility in terms of extra capacity to be able to take care of contingencies, as the colleagues presented last week. Now we have transmission assets in Eskom. I like the picture at the top here. I got this from my my managers in Eskom. They love this new innovation of this tower that is almost invisible, a cross-rope tower. Also I have an example of assets inside a substation. This picture you saw from Teboho last time just reinforces the assets in the transmission and distribution environment. And on the right, the bubbles talk about the regulatory asset base that you get. And please don't crucify me if the numbers are not 100% accurate. You can also go onto the NESA website and look at their last reason for decision. They are called RFD documents. And in those documents, they analyze Eskom's tariff submission in detail and explain their determination and the reasons. And that is where I got those figures from. So if I'm off, my apologies. So types of assets that we deal with on the left is in the yard, in a substation, with all sorts of equipment, your steel lattice gantries for receiving the conductors from the lines. We've got all sorts of equipment in there. We've got instrument transformers, circuit breakers, surge arresters, and so on. And on the right is a whole batch of cabinets that house protection schemes and sometimes metering, telecontrol equipment, and so on. But this is more light current stuff that does the intelligence that then controls the big things in the yard, that some of which you see on the left. This is overhead lines, a guide V structure on the left in a beautiful setting there, and on the right hand side you can see a close-up of the top of a tower with colleagues replacing actually a similar type of string of insulators, a V-type string. So this is the magnitude and the size of the infrastructure. Some of these things are hanging 60 meters above ground or even more. And then we have this concept of asset health that I wanted to talk about. And I like the word health. And I've used graphics of a human being on the left-hand side because it's a very carefully chosen word. And for human beings, we talk of lung capacity at the bottom here. We talk of your temperature, your respiration rate, your heart rate, your blood pressure. These are proxy indicators of the state of your health. And of course, we jog, we exercise, we try and eat well to maintain our health. But we eventually deteriorate, much as we may not want. So assets are very similar. And I've taken an example here of transformers, and this graphic shows all sorts of sensing and measuring that is done at different parts of the transformer to try and get these proxy indicators of the status of health. And on the active part there inside the oil, of course, we check for dissolved gases. These gases are proxy indicators that your transformer may be susceptible to faulting and explosion. We check moisture as well in the paper. Moisture is also not preferred in a transformer because it weakens the insulation. We also check the electric strength of the oil as a dielectric. Is it maintaining its properties, and so on. And of course, on the tap changer, for instance, similar things on the gas, but we could be monitoring the motor drive current to see how much work is it doing as it powers itself to tap at different settings, and so on. Other auxiliaries like fans, we can look at cooling controls and so on. And for the bushing, which is really the receiver of the voltage and helps you to keep the insulation with the tank so that you don't have the flushing over. This bushing is a very, very important part of the accessories, and it also deteriorates on its own. So we measure it for its capacitive properties with a tan delta test as well. And then we also check that there are no partial discharges with some sharp edges that could be compromising the insulation. So this is a bit of an analogy between the human body and what you could test for in your annual medical check, as well as what we regularly look for in one of our most strategic assets, which is a power transformer. These are some of the instruments that we fit on the transformer to determine the level of gases, online gas analyzer. I asked my colleagues at the research labs in Rocheville to give me some more pictures of instruments that we use to do one test or the other that is used to monitor the health of transformers. And you can see dissolved gases in the lab replacing the instrument that you saw in the instruments you saw in the previous slide. At the bottom is a Carl Fisher instrument, which will tell you water content, and on the right is a furanic analysis, which is a proxy of the aging of the paper that you find in the oil. And next two instruments will show you interfacial tension, a characteristic of the oil, is it maintaining its properties? And on the right-hand side is degree of polymerization, which is a test we do on paper samples, paper being the insulation medium that covers the windings in a transformer. So there are lots of tests that are done and monitored, and from those we interpret the condition of a transformer. Now, the asset health of a transformer, we have lots of organizations around the world that present best practices. And on the left-hand side is one of the accepted best practices for transformers. If you look at insulation aging of the transformer, and you weight it at 40%, then conduct a whole series of electrical tests, some of which one of the popular ones is called an SFRA, which is a digital footprint of how the windings react to impulses, and it's a proxy of saying the winding hasn't changed over time if that digital signature is remaining constant. Then you have dissolved gases in oil I've spoken about, and auxiliary components like bushings, step changers, and fans, and so on. But it's very difficult to get all these tests. In fact, in some cases, it's impossible. If you haven't done an SFRA when you bought your transformer, it's probably too late, because any SFRA footprint you get now has got no baseline for comparison. So generally, and then a lot of these electrical tests as well, you may need outages to do. So generally, we use what are called abbreviated tests, and then in ESCOM recently, we've been using the insulation aging taken from the DP paper samples as well as the oil, and also dissolved gases. They are called total dissolved combustible gases. So we look at their prevalence in percentage as well as the rate of rise since we last measured and so on. And of course, in the future, we are interested in bushings, because we are seeing that sometimes our transformers fail, not because of anything wrong with the transformer, but in fact because of the bushing. These are some of the results from our previous, the most recent of 2019. I like this picture. Unfortunately, I didn't have time to show you the one from 2011, 2013, but essentially we have made the situation better. You know, we are now on to what is called phase 3 of the high-risk transformer project, and phase 1 was over 30 units, and phase 2 similar, about 21 units, if I'm not mistaken. And we have taken out of the system those transformers that we concluded through some scientific process were irrecoverable in terms of their condition. So you will see one red one, one very poor one, and the orange would be poor, but we can live with them. The yellows are fair, the greens are good, and the blues are in fact very good. And you can see the age profile at the bottom here. So, you know, someone tells you a transformer lasts 45 years, it's not totally true. You can get a bit more than that. The next slide shows another class of equipment. On the left is live tank breakers, and on the right top is dead tank breakers. Essentially, these are circuit breakers that will respond when there is a problem and protect your equipment upstream. And this is just an example of those. The next slide shows how we compile the health index for circuit breakers. The top 3 are the parameters we worry a lot about: age, number of operations, and maintainability. And then we've got some amplifiers here. I call them amplifiers, characteristic 4 and 5. If it's underrated where it's been deployed, then we have a problem, and we amplify that situation, and we say, look, regardless of how healthy it may have been at the top, it's in the wrong place, because it will not withstand full faults if they should happen, as an example, because the kiloamp rating of the site is much, much higher. The breaker will simply explode and be obliterated. And also, if we have unresolved inherent problems, then we amplify that situation and we say, regardless of how healthy it looks, we recommend that you remove it and redeploy it. Of course, you don't have to throw it away if it's in a good condition. I will leave the explanation of the slide to these words here. We don't have to read everything in here. These are the latest results for circuit breakers. Looking very good, especially with the younger ones, but you can see that we have got some very poor red ones that are also pretty young. And yes, you do get this sometimes with OEMs, especially when they innovate and change technologies or do a lot of value engineering. Sometimes they cut too close to the bone. And we are the utility that experiences those problems, and then we talk to them, and sometimes they revise the engineering of their product, and sometimes recall them and actually replace them. So this is the picture here, but as you would expect, the high risk ones are generally towards the older generation. This picture is a summary of station assets. We've done this since 10 years ago, and believe me also when I say it's looking better. It's a very nice picture that normalizes to the same population 100%, the proportion of each category. And you can see that those transformers, the numbers I'm showing you at the top, are the very ones you saw on the previous slide. We are worried about circuit breakers that I've just shown. They've got a big red bar, 487 of them. We are also worried about CTs, current transformers. A whole percentage of them, close to a third, are worrying us. But some asset classes are not too bad. Asset risk is the concept I want to introduce, and then we are almost at the end of my offering. So ISO 55,000 talks of risk as the effect of uncertainty on objectives. You've got infrastructure, you'd like it to be completely capable all the time, but of course you've got risk of it failing because of poor maintenance or replacement not being timely, or because its capacity has been exceeded due to growth or due to lack of flexibility and so on. So there is the concept of risk, and it's defined as the probability of failure of the asset multiplied by the consequence. So you will see in the equation here, and then we break down the probability of failure into probability of that catastrophic event happening, and the probability that you are going to have failure during that event, and then the consequence of both the event and failure eventuating. And we interpret the consequence in dollars and rands, therefore multiplied by the probability. Risk is in rands. And so risk managers are managing the unwanted costs out of your business. And in other literature, you will see that the probability of failure is shown as a function of the probability. There are two probabilities. One is a failure probability based on age, which is generally obtained from history and comparison with other peers. And then there is a probability of failure based on your asset health. And this is unique to you because your assets may be aging quicker than your peer if you are stressing them more or doing bad maintenance, but the opposite could also be true. So yes, risk is measured in dollars and rands, and generally risk increases as the asset ages. So these two pictures are showing the curve for the probability of failure by age, which is in fact obtained from this very popular bathtub curve. Towards the end of the bathtub curve is where you get this increasing failure after you are done with infant mortality and constant failure rate. Most assets fail like this. Of course, others, like Deboko showed you last week, have a different failure pattern. But generally, assets increase, the failure rate of assets increases with age. And this picture is essentially explaining, on the left, is essentially explaining the onset of that bathtub curve, which then becomes a normal distribution curve as your population is weeded out. This is the result of risk eventuating. This is what you want to avoid. It's the most expensive situation. If you let your assets fail, all the expenditure you are trying to avoid, you are going to spend and more. So good risk management, good asset management avoids these situations and leads to the cost of running your operations being manageable. So I've said the financial evaluation methods of determining renewal decisions are not enough. They are not enough. We know them: NPV, equivalent annual cost, internal rate of return. On their own, they are not enough. And this is where engineering meets finance. Last week, a colleague of ours was asking Can you show me where engineering analysis only has been used to determine asset replacement? You will never find that anywhere. Of course, 2 weeks back, or a few weeks ago, we heard of a rich utility in the Middle East that will replace assets when they reach the technical end of life. They have that luxury, they've got money, but not many of us can say GIS equipment is 25 years old, replace all of it. No, we don't have that luxury. So the ultimate decision is a mix of engineering analysis and finance. The two meet and you have a new science of risk analysis in determining asset replacement. What we are trying is to answer this essential question. What level of risk triggers a replacement decision? I'm introducing a concept called equivalent annual cost. I'm giving you an answer now. The good practice of determining the right time to change your asset and to count your losses, so to say, even if it hasn't failed, is when the annualized life cycle cost reaches a minimum. So on the left-hand side of the yellow spot here, the red yellow spot, on the left-hand side, the capital cost is still significant in the total annualized cost of the asset as you are depreciating it. And generally, your maintenance cost and risk of failure is low. But as soon as you pass that spot, your capital annualized capital cost is now much less than the risk of the asset. And generally, we say that beyond that, you really need to start taking a decision of replacing your asset. That spot at which the annualized life cycle cost is the lowest is in fact referred to as the equivalent annual cost. So they say it's similar to your annuity that you would pay if you were to take a premium for someone to run these operations for you. This is the annual amount you would pay them to build all their benefit to the left of the dot when the asset is cost very little to maintain and is not likely to fail, as well as the risk to the right. You pay a flat amount, that's what you get. And on the right-hand side, if someone says, but I don't have all the data around the initial cost of the asset, the right exercise to do is to actually look at marginal cost for each year going forward. And as soon as that marginal cost exceeds the equivalent annual cost, then in fact, you are better off replacing the asset. For a utility such as ours with many sites, we've got many assets, many sites, and so you will see that I'm saying total risk per site is really an addition of these intolerable risks which are above the equivalent annual cost. If you have a blue, you are lucky you are to the left of that red dot. Unfortunately, the blue does not dilute the red. You are just lucky to have a blue, but you don't get a dilution the more blue you get. No, risk is risk, especially in a linear form. 1 point of weakness in a line, regardless of what the asset ahead or behind looks like, you are still vulnerable. So that is why you will see that, in fact, I've chosen this site, which doesn't have a name, to have the darkest red, even though it's got one of the bluest blue. So this is the way to look at your installations. In Eskom, we call it CCRA approach. We'll take all assets, we'll add all risks. And if we do this correctly, we'll have a dollar or a rand value that tells us the risk, total risk at every installation. How do we replace assets? I was saying, well, you could have a very easy answer right from the beginning and say, look, we have got infant mortality here. We didn't spec this thing right, or it's got a fatal flaw. Or you could say economic life has been reached. Or you could get to a point where we say, look, the cost of refurbing this thing is higher than it's worth. This is what is called the spend limit decision. But generally, you will run your asset until you reach one of these decisions that that forces you to change it. And even as you change it on the right-hand side, you don't just throw it away. You look at options for redeployment, as I said, with underrated equipment. But of course, if you can't redeploy it and recondition it to even redeploy it later, then you dispose of it. And finally, as I get towards the end, people always say, but we don't have enough CAPEX. And that is all good and well. There is also a recommended scientific approach for determining the prioritization of these investments. I think my colleague, my good friend, Aubrey from Canada, Vancouver, Canada, is joining us next week to talk about prioritization of investments. But a sneak preview is that you will consider a benefit to cost ratio. And essentially, you are looking at the area of that triangle I've got at the top right there. The benefit is the difference in the marginal operating cost and the risk cost. That's that triangle above the EAL straight line. That the difference in that gap between having a new asset next year and this year. And to me, I say that is the darkest risk, obviously the biggest triangle. And you will divide that with the annuity for your investment. That's the equivalent annual payment for the project that will fix the problem. And the one with the highest ratio is the project to go for. So that is the quick answer. In conclusion, from my side, I have shown you that a regime of asset condition assessment is part of determining refurbishment needs. If you don't have that, I don't think you are probably doing a good job. Secondly, asset condition should be linked to asset risk in a scientific way. And asset risk being in dollars and rands. And unless you are talking about your asset risk in dollars and rands, your story is not complete. I've said this to my colleagues in ESCOM. Our story is not complete as long as you are trying to fight for CAPEX using language other than risk in dollars and rands. Decisions of asset renewal must be based on economics of the marginal annual cost versus risk. The difference between the two. And if risk is now much higher than the marginal cost, these are the collection of the excess costs that I'm tolerating that I should not be. And lastly, projects that have the highest benefit cost ratio are the ones to be prioritized where we have a shortage of CAPEX. So that is my offering, colleagues, and I'm going to move you over to Aubrey for his view on water assets. Thank you.
Good evening, colleagues. Just a reminder, my name is Aubrey Nxuamal. Prince has said a lot. He's laid the ground. I'll just go and start running. My presentation is mainly on the pipeline assets, the replacement and augmentation drivers based on the risks inspection approach. The number of pipelines in Gauteng, because this is based mainly in Gauteng, you've got your municipalities and then you've got your water boards. My presentation will mainly focus on the bulk water pipelines, which is managed by the water boards. The bulk of the pipeline is managed by the municipalities, and they, in terms of diameters, they're actually smaller than the bulk pipeline. The content of my presentation, I'll just give an overview of the bulk water pipelines. I'll talk about the end-of-life triggers, the importance and the ones that we're using for pipelines. I'll then look at the augmentation strategies driven by capacity assessment. I'll look at the renewal strategies driven by condition assessment, and then the risk-based inspection as part of condition assessment, using a technique called external corrosion direct assessment. That is the technique that will then lead us to the engineering evaluation of the assessment, as Prince was saying, the clever engineering part of it, and the most important part of it. And then we do a risk assessment, because these assets, basically, they are those that, we use different maintenance strategies. Some of them, we can run them to failure. Some of them we need to apply, use proactive inspections. And therefore, we look at the risk assessment of these assets so that we can determine which maintenance strategies do we employ. And therefore, we look at the renewal techniques and mainly on those that are critical. The Gauteng city basically has got about 3,500 kilometers of bulk water pipeline, mainly large diameter pipeline, providing potable water to the three metros, Ekurhuleni, City of Tshwane, and the Joburg, and the two district municipalities, that is the West Rand and the City Bing, and far afield as the Northwest Province and the Mpumalanga Province and the Free State Province. And the water is drawn from the Vaal River system, and it's actually purified in Vereeniging and Suikerbosch Station. These are the two only purification stations. You can appreciate the fact that the point of supply from these two areas up to the final point is about 300 kilometers in distance. And therefore, if you consider the diameter of this pipeline ranging between 600 millimeters to 3,500 millimeters, they should be operating at a very high pressures. The lowest pressure being 5 bars, the maximum pressure being just around 35 bars. That's how high it operates. For these pipelines, the 94% of these pipelines are steel pipelines, which is the area of interest. 6% they are pre-stressed concrete. At the moment, the drive is to get rid of the pre-stressed concrete so that we remain with the steel pipelines. It's easy to maintain, so to speak. Looking at the age profile of this pipeline, for steel pipeline, the utilities normally have a design life, and depending on the material of the pipeline, they assign. And I say assign because for engineers, especially corrosion engineers, these are trivial figures. They're more important to the accountants. They assign 65 to 75 years for steel pipelines, 40 to 45 years for pre-stressed concrete. In Gauteng, currently for the bulk water pipeline, you can see in the age distribution. The ancient ones, over 250 kilometers. The not so young adults, they are over 500 kilometers. The youth brigade, basically, they just over 2,000 kilometers. There's quite a number of them, and then the young adults are around over 600 kilometers. The carrying value for these assets is about 7 billion, and the replacement value is around 75 billion. Looking at the end of life triggers as part of the life asset management, looking at the renewal and augmentation drivers as part of the end of life triggers, just want to remove this a little bit. Yeah. For renewal, for augmentation strategies, basically, you look at the end of service life triggers and the supply life triggers. The service life is mainly driven by capacity, and the supply life, which is mainly demand, supply and demand, is driven by the capacity. The service life is driven by the capability, I meant to say. And the capability driven ones are more internal factors, and they affect mainly the entire plant. Typical example would be you have a pump that the capacity of the pump is basically maybe not enough for the type of pipelines or the size of the pipeline that you have, and therefore for you to augment the pipeline, you then have to augment the pump as well. Or the water quality is maybe has changed, and you've got to augment the dosing pumps, but at the same time you've got to augment the pipeline. So that that cut across one or two assets. The end of service life, then this one is driven mainly by external factors that drives the augmentation, and this talks to the volumetric of the assets, how much you can pump on that, and it's capacity driven. It's a critical one that we'll look at for augmentation. And then we move to renewal. Renewal, which is my favorite subject, it's driven by the end of physical life and end of the economical life. Now, on the economical life, in most cases, I think Prince has touched on this as well. It links quite a lot with the financial people. They like it. In most cases, you'd find that the current value of future cash flows of your asset has deteriorated so much due to the level of maintenance that you have, such that your book value is actually now much higher than what you can recover if you had to sell this asset. And for the size of our asset, unfortunately, we do not have an active market. So we don't necessarily assign a scrap value. We just use the value in use. So when we look at them, we look at the recoverable amount. If that goes far beyond the book value, that means the amount of money that you're getting, it's not worth you moving with the asset. I think the benchmark is about 3% of the asset replacement cost that you look at, and that is your maintenance over your replacement cost. If that is over 3%, the ratio is over 3%, it's not worth really maintaining your asset. So that is cost driven. And if we look at the physical life now, this is where the asset could fail prematurely. This is the asset when it's non-functional at all, and it's driven by the condition assessment. Now these two, it's a matter of a cause and effect. The high cost of maintenance is the effect of physical life or condition deterioration. This can be sort of interpreted on a life cycle curve. These are very common. One must say these are not really applicable to pipeline. We like to use them. They give a good indication, and when we start using them for pipelines, we then we use them, and we then use the principle of your pipeline is as weak as your as strong as your weakest link, because pipeline are long line item. You're not looking at the whole pipeline and try to put it on a curve. You must look at the different sections of the pipeline. But coming back to the curve itself, you'd see, as Prince has spoken about the bathtub curve, which then indicates the cost, the economical failure of the pipeline. This is the economies of the pipeline, and we look at the deterioration curve. This indicates indicating the condition of the pipeline, and as time goes by, you can then reach a point where your pipeline fails, and where you reach a break-even point, that is when you look at the replacement cost versus the maintenance cost of the pipeline. If the value is too high, it might not be economical for you to run the pipeline. At the same time, your condition of the pipeline might be affected so much that you need to look at the replacement or augmentation. Again, these are they're not necessarily non-mutually exclusive. It can be a combination of the two strategies. Okay. Oh, I've missed this slide. Looking at the augmentation strategies in more details, as I said, it's driven by supply and demand trends, and we mainly focus on, as I said, the capacity end of life. And then we look at the social trends, economic trends, environmental trends, and technological trends. As you can see, these are more external factors. As I said, they drive the supply life, whereas the internal factors drive the service life of the pipeline. So we focus mainly for bulk water on the external trends. We conduct surveys to find out if the municipalities, are they growing? Is there growth in the area? Is it going to cause demand on our pipelines? So we look at mainly these two trends. We look at the if there's an increase in the household. We know that in Gauteng there's quite a number of RTPs coming. There's quite a number of informal settlements that are mushrooming, and we need to look at the growth as well as the urbanization of the city. That affects the economic investment in the area. When we then look at that, then we look at the capacity of our systems. As you can see, the black line here indicating the capacity of our systems, the red line indicating the peak day demand. When you analyze your data, you look at what is the demand per day in terms of the water that you're supplying to the people. The green line here indicating the annualized average daily demand. On an annual basis, how much water did you supply to the people? When we draw this curve, and these two curves are based on historical data, coming long way back, they combine them, extrapolate, and they see the rate of growth. The current rate of growth in Gauteng is about 1.7%. When you then look at this data, you then plot the values that you have. Now, you do not want the supply curve to be underneath any of this curve, particularly the daily demand. You don't want that to happen. You can still allow it for a little bit. That means you will then run your systems at a non-sustainable environment. It becomes even critical when now you're under the annualized average daily demand. But that is a situation where you've got a systems failure, and then you need to upgrade your systems, as I indicated. But in most cases, as you run your systems constantly without doing any augmentation processes, you then reach a point where then you realize that you then need to augment, and that this curve then determines the profile. The profile dictates the nature, the location, and the extent of future infrastructure augmentation that you need to do, and then you do as required onto the system itself, and that explains the augmentation processes. Now, getting to the most exciting one, the renewal strategies. Now, the renewal strategies is driven mainly by the engineers on the asset management side. The augmentation side is driven by the planning side, but this is driven by the engineers. It applies a lot of engineering evaluation as well. The recent technologies and data analytics, they've allowed engineers to utilize asset management programs to do risk-based inspection approaches, performing condition assessment using a number of different techniques. The first point of that is you then look at you analyze the historical data. Once you've analyzed the historical data, you look at the parameters of your pipeline. Is it a steel pipeline? Is it a pre-stressed concrete pipeline? What types of joint you have? Some pipes are continuously welded. Some pipes are sort of spigot and socket jointed, that is lead coke jointed. Look at all that information, the age of the pipeline, the maintenance history, the failure history of the pipeline. After you've done the failure history of the pipeline, then you look at the condition assessment approach that you need to employ on the pipeline. In most cases, you're looking for something that is very cost effective. And you see, when you do condition assessment, looking at the risk-based techniques, we look at the cost of that. In most cases, we do the terrain assessment. This is just a typical visual inspection on the manholes, and you can see the cost, the relative cost of that technology is low. You look at the soil testing, DCVG. This is direct current voltage gradient technique that you look at. These are overland techniques that you use, basically because pipelines are not visible to the eye and you don't see them most of the time. You look at technologies that would give you much more information without having to touch the pipeline. And some of the technologies, these technologies that are a little bit costly versus these are the ones that most of them are intrusive. Some of them they're non-invasive, but they could be disruptive in the sense that you need to insert a tool inside the pipeline. And then you look at the wall pipeline. Those are the techniques you use. After that, you then do your risk assessment. The benefits of that, you can, the structural remaining useful life, the prevention in terms of failure, the information, all the information you get on that, you then put it on the GIS system, and that will give you your risk. When you do condition assessment, as I said, pipelines are long line static asset and exposed to all different ground conditions along the entire length. It is important to conduct this condition assessment to predict the failure mode and risk exposure in different environment of the pipeline. The most common failure mode that we get is electrochemical corrosion, which is influenced by the soil type. I'm not going to go through, trying to explain what corrosion is all about, but yes, you're losing your electrons in the pipeline and you end up with a very non-welcoming hole on the steel pipeline. External direct assessment corrosion, it's a technique that we use in most cases to do our inspection. This is a technique that is sanctioned by the National Association of Corrosion Engineers, standard practice 0502. It is highly recommended. And when you do it, you can look at the visual inspection along the pipeline. You do indirect inspection using basic overland tools. As I've mentioned, they're the cheapest. And these tools include soil resistivity using a 4-pin method, direct current voltage gradient method. This method, basically, when you protect your pipeline against this corrosion, you inject electricity in the pipeline. And when you inject electricity, given the pipeline that is got a coat, given the fact that the pipe is got a coating, you then have a voltage gradient that will build up wherever you have a coating defect. And you can pick that up by just literally walking on top of the pipeline with probes, having copper sulfate half cells at the end, having a high resistance voltmeter here, analog one, and the needle leads you to a voltage gradient increases, and you can pick up your coating defects. You do what we call closed interval potential survey. Now, because you've injected current on the pipeline, you then affecting the voltage of the pipeline, and that is the potential of the pipeline. Under normal circumstances, a new pipeline, the potential is minus 0.5 volt. Once you inject current, you're increasing that to a high electronegative number. According to the NACE, National Association of Corrosion Engineers, SP0169, any pipeline, for pipeline to be protected, you must achieve, at least if you look at this diagram here, this red line, you must achieve at least minus 850 millivolts. Then you say, then your pipeline is protected. So when you do this closed interval potential survey, you're monitoring to see whether you are within that range. And now these two techniques, as you can see in this diagram here, this is your DCVG, this is your SIPS technique. In most cases, you'll have a simple curve like the one you see here. It'll be a straight line curve. Here you'll have a bit of up and down. This is mainly because of the soil conditions, changes all over the place. However, when you reach a point, this shows protection. The SIPS measures the voltage on the pipeline in terms of protection. The DCVG measures the coating, the integrity of the coating. This is the integrity of the pipeline protection. This is the integrity of the coating. So you expect to have something constant. Once you have a dip, like you see here, that indicates a dip, it shows then, this shows you've got a coating defect. This shows that your pipe is not protected. Now, that becomes a bit of a concern. And if you've done your soil resistivity in an area where your soil resistivity is very low, it means the rate of corrosion is very high. And in most cases in this environment, you'll find that if you open up your pipeline, this is what you would see. your pipe corroding because your coating defect your coating is gone. And if you go further on, you can see there's another one here. You can see the magnitude differs to a certain extent. Now, under certain condition, you might find that it's not necessarily a coating defect. It's not an open coating defect, but it's a it's a coating that has been affected by soil, or as you see from the next slide, it could be affected by AC high powered voltage. That is your SIPs and TCVG. Once you've done this, you do a stray current monitoring system. We'll show on the other side. According to NACE, any of the three techniques that you do, it's good enough for you to then do your evaluation. There's quite a number of techniques, but any of the three, according to NACE, it's just good enough for you to do the evaluation and then qualify your results. In most cases, these ones are indirect inspection. Then you can do a direct inspection. Then direct inspection becomes a little bit expensive in a sense that you've got to now open up the pipe. You can use the guided ultrasonic long range, or you can use the C-scan just to see the amount of corrosion. That means you can determine the corrosion on the pipeline or the metal loss without having to open up the entire pipeline. You can do that. Once you have all this information, you combine the information, you do an engineering evaluation, and then you plot your pipeline either on the GIS or on the pipeline integrity management system that you could be using. This slide shows the external corrosion direct assessment, what happens and what causes that the corrosion. This becomes an important part of the inspection, because if you know that your pipeline is actually corroding and it's failing your metal underground, you need to understand why is it failing, what is the cause of that, and you need to then mitigate, because it's pointless trying to replace or rehabilitate your pipeline without knowing what is the cause, because in a few months time, few days time, you would have the same issue. So you need to understand. So in most cases, you see the main cause of corrosion on the pipeline, it's the rail system, and it's the rail system that will then impact the stray current. It brings stray current onto the rail. As you've seen on the other slide, you do stray current measurements. You put loggers for 24 hours. You monitor your stray current activity on the rail. Now, when you monitor your stray current, the outcome that you would see after about 24 hours is typical graph that like these two graphs. This one graph, which shows values that are more electronegative, but you can see the peaks and the troughs that you have, indicates the stray current jumping on and off onto your pipeline. A typical of this drawing. In this case here, you have your stray currents coming onto your pipeline. It shows this typical on and off, and how you determine that, you'll see it's more electronegative than the potential of the pipeline. On the other side, close to the substation, now the cause of this is when they move the carriage, they use current. So it'll be a amount of current that moves the carriage of the railway. And then the return path of that is supposed to be the other rail on the other side. Now, these rails are not continuous. They use copper cables to make them continuous, but these copper cables, they then get chopped and they disappear in some stages. So when the current uses the return path, it then jumps onto the ground and look for the easiest path back to the substation. And your pipeline, in most cases, which is a metallic structure and is a conductor, happens to be then your path back to the substation. So it uses your pipeline. As it jumps onto the pipeline, on the pickup point, your pipeline would behave as if it's protected with a high amount of current. Sometimes it could be detrimental. If it becomes too high, it becomes detrimental for your coating. But as it jumps off, as it gets close to the substation, it then jumps off your pipeline back to the substation. And this is the point of interest, because at this point, your pipeline becomes completely not protected. And this is where it causes a spark. It then bends your pipeline and you have a hole. This is a typical hole that you'll find on the pipeline due to what you call DC stray current. This is direct current, stray current due to the rail system. You'd have that. But on the other hand, and this is the interesting part, because this happens when you have a huge coating defect on the pipeline. So because of that, particularly in South Africa, this is very unique to South Africa. I think the other country that has got a lot of stray currents is Australia. The reason being, we use a lot of DC rails, whereas other countries use an AC rail. I mean, Gautrain is the one rail that is AC, but most of our rails are DC, and DC is detrimental to steel pipelines underground. So this is why stray current is the biggest issue in South Africa. So because of that, then we've moved to better and the greatest coating systems that we have, one of them being a triple layer coating system. But now the paradox is the more your coating is much better. Now we've moved from DC corrosion to AC corrosion, because you've got a very small hole or a small coating defect, but the small coating defect, the current due to AC, mainly coming from the overhead power lines, using two techniques, two systems that would impart current on your pipelines. One would be the electrostatic induction, that is due to fault condition. You then have, due to faulty condition, you then have your current coming onto the path, and then it goes onto the pipeline. And this is for a very short amount of time. But if you have a very small defect here, the current density becomes quite a lot for the pipeline to handle. If it's a very good coating, you'd have this situation where you have the coating stress. If it's not a very good coating, then you have this kind of coating melting. The other one being the electromagnetic induction on your pipeline. That is, the pipeline would be in the servitude of your magnetic field. Then it creates an induced current that will then be in the pipeline, which then becomes the same issue. So that's how the pipeline. Then once you've done your stray current monitoring, you've done your DCVG information, you've got your DCVG information, you've done your soil resistivity as well. You then plot all this information in one graph, and that is your engineering evaluation. Once all this is plotted, again, given the fact that the pipeline is long, I mean, you can see, sometimes some of this pipeline could be 40 kilometers long. Once you've plotted all this information, all that you want, if you look at the DCVG, you want areas where you have high coating defect, that is show coating defect. The green one showing just small coating defect. The blue one is just the coating defect is moderate. The red ones, like this one, showing high, very high coating defects. You look at the soil resistivities. The red one is highly corrosive environment. The blue one is moderately corrosive. The green one is non-corrosive environment. And then you look at your SIPs where your pipeline is not protected. In most cases, you find that areas like this are mainly affected by stray current, hence a lot of peaks that you see. This one is much more important. This area here shows protection. This area underneath here shows non-protection. So once you've seen areas like this, these are areas that you pay because there's a bit of non-protection here. The soil is corrosive here. You've got quite a number of peaks. There's even a red one that shows that you've got a coating defect. You then select that. Now, this helps you because you don't have to inspect the entire pipeline now, or you don't have to replace the entire pipeline. You just replace sections of pipelines instead of the entire pipeline. And this is the area with the highest risk of the pipeline. Furthermore, what you do, you then look at, on the GIS system, you plot the high area, the risk area, maybe with different colors. You can use green here as a low risk, the bluish color here as a high risk. maybe the purple color here as a medium risk area. You then do your risk assessment. Prince has gone into details in terms of explaining your risk assessment in terms of probability and consequence of failure. But the way we do it on our side is the consequence will be mainly driven by, is this pipeline in a critical area? Should this pipeline fail, will it affect the environment? Will it affect the health of the people, safety of the people? And will it affect the operational capability of the pipeline? If all those are true, and then your risk exposure is high, you look at that, and that's a section that you select to do further tests. Then you do your direct assessment on that. You use your guided ultrasonics. In your guided ultrasonics, it's just a small area that you open up. If you open up this small area, this belt here has got transducers. These transducers, they go underneath the ground. You don't have to open up a huge area, but you can inspect up to 500 meters on either side of your belt. Like you can see here, your belt is here. You can inspect all the way up to this side and all the way up to that side. Only this area being exposed, not the entire pipeline. But that the transducers, the current, the wavelength that goes through these transducers and goes to a pipeline, it can indicate where you have corrosion. It can pick up the welding. It can pick up any structure that touches your pipeline, foreign structure that touches your pipeline, and it can pick up a corrosive environment. If it picks up a corrosion here, it tells you how deep is your corrosion. Typically here, you can see now how much metal loss you've lost. And according to the standard, if you've lost more than 80% of your metal, then you can replace that section of the pipeline. But if you lost maybe less than that, 60%, then you determine your frequency of inspection. You can always calculate the corrosion rate given the fact that you know when the pipeline was installed, and you know the diameter and you know the remaining diameter. Then you can calculate the corrosion rate per year, and you can determine when to do the next inspection. However, if this is more than 80% of your remaining metal, you then need to replace the pipe. Now, the replacement techniques that you use, if you've gone through your metal, you can repair it. That means you've got a hole and you're probably leaking, your pipe would probably be leaking, and then we then use a wooden plug. If the pipeline is not leaking, but you suspect the structure of the steel might not be able to carry your steel, you can then use other techniques like cured in place pipeline or closed fit lining on the pipeline, basically just putting another pipeline inside your pipeline using the main pipe as a host, just to strengthen the remaining pipeline. If the entire pipeline or section of the pipeline, you feel that even structurally this pipeline is not good enough anymore, you can then cut that section and put a new section. And this, this tells you under repair, structurally sound. Here, it can still hold. Pipeline repair, it won't hold anymore. Therefore, you need to put a new pipeline. Colleagues, for me, and that's all that is. Thank you so much.
Thank you so much, Engineer Nxuamal and Engineer Moyo. Clearly, we need to have a session or two on water alone. We cannot mix water and electricity. I have a few questions, not a few, a lot of questions, I must say, from our participants and our audience. But due to time, can I request, I've tried to answer a few of them, but I would humbly request that we send the answers via email to everybody that has sent the questions and the comments. Thank you very much for the good comments. This presentation was well received, presenters. The attendees really appreciate the information that you have shared with them this evening. So I won't go any further into the questions if you allow me, please, colleagues, just to make sure that we do end on time. The next presentation would be next week, our webinar for next week. As Prince has mentioned, it will be presented by Baldwin, and it is on project portfolio optimization. Please do join us, and I thank you very much. From Engineer Buthelezi, we shall meet next week. Thank you and goodbye.